All right, welcome back. Our next topic here in Unit 7 is the idea of solving our different trig equations. We're going to go through a bunch of different techniques to solve them. The basic idea is you're going to treat them like you treat a lot of different algebraic equations. Isolating the trig function, which might mean solving something that's linear, something that's a quadratic, other types of forms right there to get our answer. Everything is to be based on the special angles from the unit circle. So while it is certainly possible that these answers could be something that's not exact unit circle values for future classes, everything in this video and everything in our class will be solvable based on exact values. Something also to consider, since everything is constantly repeating, there's an infinite number of solutions for all the problems. The idea that if, for example, pi over 3 is one answer, we have to add on 2 pi n to accommodate for the infinite sets. Because every 2 pi, we rotating around both in positive and negative directions gets us the exact same location, so it's a valid answer. The n is just simply an integer representing how many times you're going to rotate it around. I've seen also written as 2 pi k, but it's just really the same concept right there. There'll be certain times we're going to try and see if we can condense the answers down, because they might actually have a pattern internally before we worry about the whole plus 2 pi m parts. So we'll start off straightforward. So we need to combine like terms. We subtract the sine x over, get root 2 equals negative 2 sine x. Divided by the negative 2, we have negative root 2 over 2 sine x. Based on the unit circle, sine is a negative root 2 over 2 in quadrants 3 and 4. At the pi over 4 values, 5 pi over 4 and 7 pi over 4. So we know the infinite set would be the 5 pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n. But we want to see, is there a way to combine them into one answer? So is there a pattern that connects both of them? And then connects to their coterminal angles. So the way we figured out that is very straightforward. We look at the pattern connecting the two angles currently. 5 pi over 4, 7 pi over 4. Next one is 9 pi over 4. We're increasing the numerator by 2. And we ask ourselves a very simple question. Is this coterminal back to the first? If it is, then I can connect the two of them into one answer. If it's not, then they need to be written as separate answers. And 9 pi over 4 is not coterminal back to 5 pi over 4. So therefore, they are two separate answers. So we'll write them as 5 pi over 4 plus 2 pi n, and then 7 pi over 4 plus 2 pi n. Okay, so we're always just simply seeing what's the pattern that connects the answers, and can I go back to the first? So here we'll notice we have only one trig function, but now it's being squared. We still isolate in the same kind of way, so we go ahead and add the 2 over, divide by the 3, and then square root both sides, where we have to remember solving any equation by square rooting is a plus or minus. And then rationalizing this answer gives us tangent to be plus or minus root 3 over 3. So trying to look at, okay, what are the answers for the unit circle that create tangent to be a positive and a negative root 3 over 3? Since it is plus or minus, we're going to use all 4 quadrants. And then tangent is going to be the root 3 over 3 scenario when we're dealing with the pi over 6's. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So that's our unit circle answer. Now, what is our infinite set answer? Well, we take a look at, is there a pattern that connects all 4 answers? Well, pi to 5 pi would be 4, but then 5 to 7 is 2, so there's no pattern that connects all 4 of them. So then we take a look at the diagonal pattern, because this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We see if quadrant 1 and 3 are connected, and then 2 and 4 are connected. Because there's no way for 1 and 2 to be connected to get back to being coterminal, or 2 and 3 to get back to being coterminal, or 3 and 4. So it has to be like a diagonal pattern instead. So pi over 6, 7 pi over 6. Next angle would be 13 pi over 6. Is that coterminal? Yes, it is. 13 pi over 6 is coterminal with pi over 6. So we'll write that answer as pi over 6 plus pi n. Now, why pi n? Well, the pattern that goes from pi over 6 to 7 pi over 6 is increasing by 6 pi over 6, which reduces to pi, hence pi n. The other pattern, the other angle, we have 5 pi over 6 and 11 pi over 6. Their pattern is also, again, a 6 over 6. We would get a 17 pi over 6. And again, is that coterminal back to the first, back to 5 pi over 6? Yes, it is. So our other answer would be 5 pi over 6, also plus pi n, because we're increasing by 6 pi over 6, or pi. So that's how it's going to look when we're trying to identify them together and putting them in a coterminal kind of format. Where we're reducing, instead of having 4 separate answers plus 2 pi n, we can combine 2 answers into 1 and still show everything that's going on there. So you will find a lot of times, especially if they're based on the same angle, if it's quadrant 1 and 3, you'll have it plus pi n to connect them. Quadrants 2 and 4 plus pi n also connecting them. There are other ways to connect them that are not necessarily in the diagonal quadrants, so you need to watch out for that. And you're always just simply testing what is the next angle in the pattern. Is it coterminal back to the first? All right, now for this one, we've got a couple different trig functions. And the temptation might be to just divide by the cotangent from both sides to reduce it and cancel. Problem is you can't do that. You're not allowed to just simply divide over a trig function. Really, you're not allowed to divide by any variable, because what if the variable is 0? So instead, we subtract it over, so we can factor out the common cotangent x, and then solve those expressions. So cotangent x equals 0, and then cosine squared minus 2 equals 0. So the cotangent is 0 because it's set up as cosine over sine when cosine is 0, which will occur at pi over 2 and 3 pi over 2. Whereas cosine squared minus 2 equals 0 when we can get cosine to be plus or minus root 2. Now, I had said everything was going to be based on the unit circle, and cosine being root 2, either positive or negative, is not on the unit circle. Now, had it been root 2 over 2, it would be. Or had this been secant equal root 2, that would also be on the unit circle. But cosine equal to root 2 is not on the unit circle. This actually is impossible, because both sine and cosine must fall in between -1 and +1, based on how the unit circle is set up as the x and y coordinates with radius of 1, or based on how the right triangle trig is set up as opposite over hypotenuse, or adjacent over hypotenuse, where the hypotenuse has to be the biggest side, and therefore the ratio can't be larger than 1. Either way, however you want to look at it, can't solve that part. So it's only the pi over 2 and 3 pi over 2. So we consider the next angle in the pattern to see can they be connected. And it's 5 pi over 2. And we ask, is that coterminal? Yes, it is. 5 pi over 2 is coterminal back to pi over 2. So our answer is pi over 2 plus pi n. Because going from pi over 2 to 3 pi over 2 is increasing by 2 pi over 2, which is just pi. So the biggest thing here is you're going to need to factor these expressions. You're never dividing by a trig function. You always want to set equal to 0 and factor when there's multiple expressions like that. And it could also be a traditional trinomial trig function like this one is right here. Recognizing this is equivalent to if I wrote it as 2w squared minus w minus 1. Where we can factor that as our 2w and w, 1 and 1, and recognizing it's a minus 1 and plus 1 like that. Getting w to be a -1/2 and a positive 1, which means sine is a -1/2 and sine is a positive 1. Now you don't need to rewrite the sine as w, or really any variable you want. You can recognize it's still a trinomial and factor in that kind of way. But if it helps you, feel free to rewrite a dummy variable in there, w or whatever you want, to solve it that way. Recognizing sine is a -1/2 at our 7 pi over 6 and 11 pi over 6. And then sine is 1 at pi over 2. So we take a look at, is this a connected pattern? We have to look at all three angles together. And I'm going to want to rewrite the pi over 2 as 3 pi over 6 so that I can have a common denominator to better see what my pattern is. And between all three angles, they are connected by a pattern internally. They're increasing by 4 pi over 6. Which means the next one is 15 pi over 6. which is really, when you divide it by 3, 5 pi over 2. So is that coterminal back to pi over 2, the first angle? And yes, it is. So all three angles are put together in one pattern. Our pattern always starts at the first angle, pi over 2, and it's plus the n, whatever the pattern is. So going from 3 pi over 6 to 7 pi over 6 to 11 pi over 6 is going up by 4 pi over 6, which is increasing by 2 pi over 3. All right, so the original 7 pi over 6, 11 pi over 6 would not have been connected together by themselves, but when we include pi over 2 in there, we actually do connect everything. And it's constantly repeating pattern there. It's going through a third, 2/3 of the way as we go around each time. All right, the key, trinomial factoring, and then recognizing again your pattern from there. Now here we have two different trig functions, both being squared. And there's no way to factor the way they currently look because they have nothing in common. But we do recognize that both secant and tangent are Pythagorean identities with each other. So we're going to rewrite one in terms of the other with a Pythagorean identity. Which one you want to write with? Well, it really is going to depend. Secant squared is 1 plus tangent squared. Tangent squared is secant squared minus 1. It's kind of up to you which one you think is going to work better for you. I'm just going to work with tangent, so I'm going to rewrite the secant squared as 1 plus tangent squared. Doing that gives us 3 plus 3 tangent squared minus 2 tangent squared minus 4. So combining like terms, we're going to get a tangent squared minus 1 equal to 0. So we can isolate tangents. Square root both sides, and we can see that tangent is going to equal plus or minus 1, which is all the pi over 4 values. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We would have found the same answer would have shown up if we had worked with secant squared instead, rewriting the tangent squared parts. So it really is not going to matter which one you want to go with. If you want to kind of pause the video and work through replacing tangent squared with secant squared minus 1, be my guest, then you should still get the same final answer. You'll get secant to be plus or minus root 2, which is how you're going to get these answers right here. So we then check to see if this whole pattern is coterminal. So it's increasing by 2 pi up top. So the next one is 9 pi over 4. Is that coterminal back to the beginning? Yes, it is. So all four angles are connected together by 2 pi over 4, which is pi over 2, n. All right. And don't assume everything is always connected. This has been a nice string of answers that have all connected together, so we can write a pattern. But it's also entirely possible that you get answers that don't connect at all. So then you're just doing individually each answer plus 2 pi n. Remembering if you have all four quadrants, we would only connect the diagonal quadrants if all four failed, which is what's going to happen if you work with the pi over 6s and pi over 3s. They're not all connected, but then diagonally they will be. Now for this example right here, we're recognizing we got sine and cosine. They're not multiplying together, so there's nothing to factor, but they're also not being squared, so I can't use a Pythagorean identity. But even though they are both currently not being squared, I can make them squared. So I can square both sides, recognizing that squaring cosine x plus 1 means we're doing cosine x plus 1 times cosine x plus 1. So we FOIL that to get our cosine squared plus 2 cosine x plus 1. Sine squared is just simply sine squared. So by squaring both sides, we now have our Pythagorean identities to work with. So we have to determine whether we're going to replace cosine squared or sine squared. Now, if you only have square terms, like the previous example with secant squared and tangent squared, it doesn't matter which one you work with. But if you have non-square terms, we need to make sure we replace the one that doesn't have the square term. It doesn't have the non-square term. So we have to replace the sine squared. Because if I tried replacing cosine squared, there'd still be that regular cosine there that would be unable to fix. So we replace our sine squared with 1 minus cosine squared, our Pythagorean identity. Combining like terms by adding the cosine squared over and subtracting the 1 yields 2 cosine squared x plus 2 cosine x equals 0. Where I can factor the 2 cosine x away, leaving cosine x plus 1. So this means cosine x is 0, which occurs at pi over 2 and 3 pi over 2. And then cosine x equals negative 1, which occurs at pi. Now, for each of these questions, we can't just go to our infinite set just yet. Because since we squared both sides, we do need to check to see, do we have extraneous solutions? Because if, for example, you had an equation where you had negative 2 equals 2, that's clearly false. But by squaring both sides, it becomes 4 equals 4, which looks to be true. So we need to test to see if that's actually going to occur. So we have to substitute each of these three answers back into the original pre-squared expression. So we're going to work with cosine of pi over 2 plus 1 equals sine of pi over 2. 0 plus 1 equals 1. 1 equals 1. That's okay. 3 pi over 2. So we have cosine of 3 pi over 2 plus 1 equals sine of 3 pi over 2. 0 plus 1 equals negative 1. We get 1 equal to negative 1. That's false. So 3 pi over 2 is an extraneous answer. And that's exactly what happened there. 1 and negative 1 are not the same, but when you square them, they appear to be the same. And then finally, pi, we have cosine of pi plus 1 equals sine of pi. So it gives us negative 1 plus 1 equals 0. 0 equals 0, so it's okay. So our only two answers are pi over 2 and pi. And if we try and put them together, so we see we have pi over 2 and then pi, which is 2 pi over 2 really. Next angle in the pattern is 3 pi over 2, which is a problem for two reasons. Reason number one, that's not coterminal back to pi over 2. And the other problem is, well, we just saw that 3 pi over 2 failed. So that can't be an answer because of that anyway. Which means individually, each answer is plus 2 pi n. So again, when you have a failing scenario, that the next angle in the pattern is not coterminal back to the first, there is no connecting pattern, so just plus 2 pi n for each of those problems individually. All right, so those are the 6 main types of equations you could solve. Your basic combining like terms, your square rooting, factoring, trinomial factoring, rewriting with Pythagorean identities, having to square to rewrite with Pythagorean identities, all those things are all there. But something interesting about each and every one of those problems was that every single problem's angle was just simply x. There was no coefficient to go with it. Well, that's not going to always be the case. So we have the angle now is 3x. The way we solve doesn't change whether the coefficient is there or not. So we're still adding the 1 over, still dividing by the 2. And then we see that cosine is equal to a half at our pi over 3 and 2 pi over 3. But now it's not x equals pi over 3 and 2 pi over 3, it's 3x equal to pi over 3 and 2 pi over 3. Now, we do need to divide by 3 to solve for x, but we're not going to do it yet. We divide by 3 once we set up our infinite set answer. So we check to see pi over 3 and 2 pi over 3. Next up would be 3 pi over 3. Is that coterminal back to the first? No, it is not. So we would say 3x equals pi over 3 plus 2 pi n. And we'd have it equal to 2 pi over 3 plus 2 pi n. Which means, since we need to get x by itself, everything divides by 3. So our true answer would be pi over 9 plus 2 pi over 3n, and then 2 pi over 9 plus 2 pi over 3n. So again, we're looking for our infinite set at the end. After we're done solving, we're dividing the 3 over then at that point. So do not divide the 3 over first, because it's going to mess up the whole idea of coterminal. Because once we divide by 3, even if it was supposed to work, the pattern is now altered and it's not really going to be the same kind of thing. So we're better off waiting to see, is it coterminal first? And if it is, great, rewrite our pattern. If it's not, then we don't need to worry about it. It's 2 pi n. We divide the 3 over. Because as we can see now, It's not every 2 pi we're going to get this pattern. It's going to be 2 pi over 3. We'll get a next number in this particular pattern. The coefficient could also be dividing with the x, so we have x over 2 here. We still solve it the same kind of way, so we're going to go ahead and subtract the 3 over. 3 tangent x over 2 equals negative 3. Divide by the positive 3, we get tangent of x over 2 equals negative 1, which means our angle is going to occur when tangent is negative 1, which is 3 pi over 4 and 7 pi over 4. So we're still testing to see if it's coterminal before we worry about the x over 2 parts. Well, 3 pi over 4, 7 pi over 4, the next one would be 11 pi over 4. Is that coterminal back to 3 pi over 4? Yes, it is. Another easy way to check, they're both based off the same denominator, radian answer, and they're in a diagonal quadrant, quadrants 2 and 4, so it does make sense. So we get x over 2 equals just 3 pi over 4 plus pi n, because that's our pattern, but we're trying to get x by itself, so now we multiply everything by the 2. So we get x equals 3 pi over 2 plus 2 pi n. That's our infinite set answer. All right, so more often than not, you're not really going to have a lot of problems with the coefficients in front of the x or dividing with the x, but it is a possibility, one that typically occurs more often with some of the calculus stuff as well next year, which is why we want to make sure we explore it. All right, so that's it for our trig equations. We've talked about the different basic fundamental identities and then our verifying trig proofs with these trig equations now. So everything else is going to be different types of identities, more things to essentially you're going to have to know. There's a lot of them. We'll go through the 4 different videos of each of the different individual types of identities. So I'll see everyone next time for those videos.